So what I'm claiming in step 2 here is that if we end up choosing a policy that is not based on knowing all of the transitions, like there's still some unknown transitions out there, but we end up taking a policy that puts us into a loop where we never visit any of those, then that still has to be an optimal loop. We're not making any mistakes.
Right.
It could be that we could do as well by uncovering those other values, but we can't do any better because we are assuming in step 2 that anything that we don't know has the largest possible value.
Right.
And so if it has the largest possible value and we still don't want to go there, then we're doing at least as well as optimal.
Yeah, that's kind of cute.
All right. So, but now we need step 3. So now step 3 says, okay, we solve the MDP, this sort of imagined MDP that has these optimistic estimates in it. And let's say that actually takes us to a state action pair that we haven't been to before and we learn its value.
Mm-hmm.
How many mistakes might we make en route to that? So when we actually get to that state and traverse an edge that we didn't know about, that could have been a mistake.
Right.
So that's definitely, one. And how many mistakes might we make, seeking out this state that actually turned out to be a really bad state?
From a particular state, I guess the number of states.
Yes, right. So the number of transitions that we might take just to find out that we were wrong could be as big as n.
Right.
The number of states.
Or n-1 or something like that. But yeah.
Yeah. So en route to a this isn't a deterministic MDP. En route to any state, our path is going to be either bounded by n, or if it's bigger than n, it's infinity because we're actually looping without actually getting to that other place.
Right.
So the most it can be is n, right?
Mm-hmm.
All right. So given that, we might make n mistakes to find out something new, to learn something new, to visit a state action pair that we've never seen before. How many times can that happen? How many times can it be that there's a policy that brings us to a state action pair that we haven't been to before?
How many times can that be?
Yeah. So each time this sort of step 3, maybe I should write it in English. All right. So what this step 3 is that what our RMAX algorithm tells us to do is to execute a path that actually brings us to an unknown state action pair. Then we go traverse that edge, find out what it really is, and generate a new policy. So the number of steps that it might take to get to that new state action pair is n,
Right.
and the number of times that we might discover a new state action pair is what?
N times the number of actions.
N times the number of actions, because that's the total number of unknown things in the graph to begin with.
Right.
Right. So we're exploring the MDP, and each time we visit a state and take an action we haven't taken before, that's going to reduce 1 from the count.
Mm-hmm.
So the largest that count is n times k. And so the total number of mistakes that this algorithm can make is bounded by n squared k.
Hey, that's polynomial in n and k.
It is, and it also doesn't depend on epsilon, and it also doesn't depend on delta.
That's even better. So wait, if it doesn't depend on epsilon and it doesn't depend on delta, then it means it's polynomial in those things.
Sure, yes. It's a very simple polynomial in those things.
So then we're polynomial in everything.
Yeah. So this is an efficient exploration algorithm for deterministic MDPs, right? All it's saying is whenever we don't know something, assume it's awesome, behave accordingly. If we learn something new, make note of it. And so the number of times that we take a step that might not be the best thing to do from that state can't be any bigger than n squared k.
That's beautiful.
Yeah, it's pretty cool. This kind of analysis comes from a paper that Sven Koenig wrote with Reed Simmons, where they actually analyzed Q-learning in this kind of setting, and they got a worse bound, like n cubed times k. But this algorithm is sort of pretty simple, and it gives us a nice bound, and it sort of does what you'd want it to do.
That's cool. I will point out that n cubed k is also polynomial.
Yes, but it's a slightly worse polynomial. You're absolutely right. I mean, he showed that Q-learning has a polynomial bound in these kinds of environments if you set up the rewards correctly and if you set up the initial value functions correctly. All right, so that gets us through stochastic MDPs that have no state and state MDPs that have no stochastic. And the last thing we want to dive into is what happens if we do something like RMAX except for on stochastic MDPs.
Well, we still have another case. We have to worry about the case where we have no state and we have no stochasticity.
So, okay, well, let's do that one really fast.
All right.
So you're talking about an environment that has one state and all the actions are deterministic. They give you a deterministic reward and return you to that state.
Right.
So this is essentially a deterministic bandit problem.
Right.
So how many mistakes might we, what would be an algorithm for this and how many mistakes would it make?
The dumbest one would be, or the simplest one would just be take every action once and then you know everything.
Right. And each of those, so k minus 1 of those are mistakes, possibly.
Mm-hmm.
And then, when we know that, then we just keep choosing the optimal action thereafter.
Yeah, and you could do a little bit better if you assume that everything was R max, because as soon as you come across R max, you can stop.
Very good. Yes. Right. If you end up finding along the way an action that actually gives you the full value, the full R max value, then we don't have to explore the rest of them because they're not going to be any better. Yeah. Okay. So that gives us it doesn't give us a better bound, but it does probably give us better performance if we keep track of that. So yeah, so this is a silly case.
Well, but it does allow us to do, say we solve 3 of the 4.
Great. All right. So let's dive into number 4.